So we consider an isolated conductor. Isolated conductor means in neighboring of this conductor there is no other species or thing. Means we consider an isolated conductor, just as shown in figure. Here an isolated conductor is under the influence of an applied field. Here E suffix E is an applied field, means we take an electric field, that is external electric field. In this external electric field we place an isolated conductor. So we know that the electric field is originated from some positive charge and terminate to some negative charge, and due to this the conductor having atoms, it is composed of atoms. Atoms has positive nucleus and negative electrons. Due to this there is a separation of positive and negative charge in the conductors. Means negative charge is attracted towards the positive source of electric field, and positive charge is repelled by, you can say that the positive charge is repelled by that positive source of electric field. So the positive and negative charge is induced in this conductor due to this external electric field. Now since due to free charges, means due to the free charges that is in an isolated conductor, they are accumulate on the surface of the conductor when applied external field E suffix E. Now due to the accumulation of on the surface of the conductor, they form an induced surface charge. Now due to this induced surface charge, they set up an internal induced field E suffix I. Now we know that the electric field is originate from positive charge and terminate to negative charge. Since the external field is originate from some positive source of charge and terminate to some negative source. Now due to this induced field, induced surface charge, there creates an internal electric field also, and the direction of this internal electric field is from positive to negative charge inside the conductor. Now due to this internal induced field, the internal induced field cancels the externally applied field inside the conductor. So we can say that inside the conductor electric field is 0. Due to electric field is 0, the volume charge density is also 0 inside the conductor. So there are some important properties of conductor. A perfect conductor having conductivity is equals to infinity cannot contain an electrostatic field within it. Here we see that inside the conductor the electric field is 0. There is a cancellation of external field due to this internal induced electric field. So for perfect conductor the electrostatic field within the conductor is 0. So we can say that electric field is equals to 0, and we know that electric field is related to the potential, electric potential, and the relation is electric field E is equals to minus gradient of V. So here the potential is also 0, we can say. And second point is a conductor is called equipotential body, which implies that the potential is the same everywhere in the conductor. Now according to Gauss's law, if electric field is 0 inside the conductor, then the charge density, volume charge density rho v is also 0. This is according to the Gauss's law. Now under static condition, electric field intensity is 0, volume charge density is also 0, and the potential difference is also 0. This is under static condition. Now means when the conductor is isolated, then these are the conditions that is given by equation 1. Now when the conductor is not isolated, means the conductor is connected by some external source, then the electric field is not 0 inside the conductor. Now here we consider a conductor. The conductor is basically of cylindrical shape, having cross-sectional area S, and it is connected by some external field, means connected by some source having potential V. Here this is a positive terminal and this is a negative terminal. So a conductor having a free charge, that is in the form of electrons. So these free charge, that is negative charge, is attracted towards the positive terminal of the battery, and in the direction opposite to the flow of electron, there flow an current I. That is, the direction of current I is opposite to the direction of flow of electrons, and we know that the electric field is from the direction of electric field is from positive terminal to negative terminal outside this source. So due to this setup, that is conductor is connected by some external applied field, there must be some electric field inside that conductor. That electric field inside the conductor is due to the flow of current, or that is used to sustain the flow of current. Now as electron moves, since the electron moves toward the positive terminal of a battery, they encounter some damping force. That damping force is called resistance. Resistance is a opposite force that suppresses the flow of current from positive terminal to the negative terminal. That is due to the flow of electron towards the positive terminal. So there is an resistance due to some damping force, and that resistance can be calculated with the formula that is called V upon I. So resistance is noted by capital R and it is equals to V by I. V is the potential applied across the conductor and I is the current. Now we assume that this conductor having a non-uniform cross-sectional area. This figure is a uniform cross-sectional area. We assume that if there is non-uniform cross-sectional area, then the resistance of this conductor is given as V by I, and the potential is in the form of, we know that the electric potential formula is minus E dot dl, and current in terms of current density is noted by J dot ds. So in this way we can determine the resistance when there is a non-uniform cross-sectional area. Now we know that J equals to sigma E. That is called a point form of Ohm's law. That is a Ohm's law. Now E, that is electric field. Electric field, due to this applied potential, is equals to V upon L, where L is the length of the conductor. So this is a magnitude part, that is E equals to V by L. Now since we know that the current density J equals to I upon S, current upon cross sectional area, or we know that current J equals to sigma E. So by using this we can say that I upon S equals to sigma E, because both are of formula of J, and E, in place of E we can put V upon. So here we take a ratio V upon I. So we take a ratio V upon I, and it is equals to V upon I is equals to L upon sigma S. So from here we get a formula of resistance, and this formula of resistance is when the cross sectional area S is uniform. The last formula of resistance is when the cross sectional area is non-uniform. Then we use that formula. But when the cross sectional area is uniform, we use the formula of resistance, that is equals to rho L upon S, where rho is called a resistivity of the material. Resistivity is inverse of the conductivity. Next topic is polarization in dielectrics. Now we know that the dielectrics are non-conductors. They have a few free charge for the conduction of current. Now here in this topic we talk about polarization in dielectric. How the polarization occur in dielectrics. So the charges in dielectric are not able to move freely, as we know that they are non-conductors, because they are bounded by some finite force and expect a displacement when an external force is applied. Means when a dielectric is placed in an electric field, then only charges are displaced. So the figure A is an atom, isolated atom. Atom has positive nucleus and an electrons that has a negative charge. So this is unpolarized atom of a dielectric, and this is called non-polar atom. Now when this non-polar atom is placed in some electric field, now we know that electric field has some positive source. Now due to this electric field, the structure of the atom that has nucleus and electron is displaced, that having minus q and plus q, means it has two poles, and the atom get polarized. The atom get polarized due to this electric field. So it makes some dipole. The dipole is a two pole that has minus q and plus q separated by some distance d. Here d vector. D vector is from minus q to plus q. So figure B is a polarization of this non-polar atom that is shown in figure A. So when the dipole results from the displacement of the bonded charge, the dielectric is said to be polarized. Means the dielectric initially is non-polarized, unpolarized, because the atoms are bounded by some finite force. Now Due to the influence of electric field E, that bonded atom or unpolarized atom get polarized. That means the negative electrons are attracted toward the positive source of the electric field, and a nucleus is repelled by that positive source of electric field, and it makes an dipole. So the dielectric is said to be polarized, that is due to the displacement of bound charge, and it makes a dipole. Now this dipole has some dipole moment. So dipole moment is denoted by small p, and it is a vector quantity. So p vector is called dipole moment, and the formula of dipole moment is q into d vector. Here we take a multiplication of magnitude of either of the charge and distance vector d. So this is the formula of dipole moment. Now, since the dielectric having a number of such dipoles, so here we consider an n dipoles in a volume delta V. So the total dipole moment due to this electric field is the summation of individual dipole moment. And here we take a summation from 1 to n, and that is called a total dipole moment. Now from this total dipole moment we can derive the polarization. So definition of polarization. Polarization is noted by capital P vector, while the dipole moment is noted by small p vector. This is the difference between polarization and dipole. So the polarization capital P vector is defined as the total dipole moment per unit volume. So definition of polarization is simple: the total dipole moment per unit volume. So we know that the total dipole moment is denoted in summation form, and per unit volume means here we assume that the volume has a delta V, that is a unit volume. So the ratio of total dipole moment upon unit volume, as unit volume delta V tends to 0, and that is called a polarization, that is capital P, and the unit of polarization is coulomb per meter square, because the unit of volume is meter cube, and here the unit of Q is coulomb and D is the distance, that is meter. So 1 meter is cancelled, we get coulomb per meter square. That unit is same as D vector, that is electric flux density D. Now the polarization increases the electric flux density in the material medium. Means the electric flux density in free space is denoted by D equals to epsilon E. We know that. Now when the dielectric medium is used in place of free medium, free space, then polarization, due to that polarization of dielectric, electric flux density increases, and so the electric flux density D in dielectric medium is given by as epsilon naught E plus vector P. P is here polarization. So this is the formula of electric flux density when we use a dielectric medium. Now we know that in free space there is no polarization, so D equals to epsilon E. We know that for some dielectrics polarization is directly proportional to electric field intensity. that is polarization P vector is directly proportional to E vector. So here there is a proportionality constant, that is psi E into epsilon E. Here psi E is called electric susceptibility. That electric susceptibility is of the material which is used for the dielectric. It is more or less a measure of high susceptible. Susceptible means sensitive. It is a measure of high sensitive a given dielectric is to electric field. So simply the polarization formula in terms of electric susceptibility is P equals to psi E epsilon naught E, and psi is a sensitivity factor. Next is dielectric constant and strength. Now we know that the electric flux density D in case of dielectric is given by equation this one, that is D equals to epsilon E plus P vector. Now in terms of electric susceptibility, the polarization is equals to psi E epsilon naught E. So we put it in above equation. So we get this form, and here we take common terms. So here we get a term within bracket, that is 1 plus psi E. That 1 plus psi is epsilon R. Okay, so this electric flux density D equals to epsilon naught epsilon R E, and epsilon naught into epsilon R is simply epsilon. So epsilon equals to epsilon naught epsilon R. So this epsilon is called permittivity of the dielectric. Epsilon naught is the permittivity of free space, that is epsilon naught, and epsilon R is called a relative permittivity of the dielectric constant. This epsilon R is equals to 1 plus psi E, and the permittivity of free space epsilon naught has a constant value, that is 10 to the power minus 9 upon 36 pi farad per meter. Now since the relative permittivity and electric susceptibility is dimensionless, where the unit of epsilon and epsilon naught is farad per meter. Now what is the strength of a dielectric? The dielectric strength is the maximum electric field that a dielectric can tolerate or withstand without electric breakdown. So dielectric strength is the maximum electric field that dielectric can tolerate without electric breakdown. Now what is electric breakdown? Dielectric breakdown or electric breakdown is said to occur when dielectric becomes conducting. Means the dielectric become conductor. That is due to an electric breakdown.